In this video, we're going to determine how to predict whether a precipitate will form in a chemical reaction. So when two ionic compounds that are both in aqueous solution are mixed or reacted, how can we predict if a precipitate will form? So for example, if we mixed aqueous sodium chloride and aqueous silver nitrate, would one of the products precipitate out? Well, the first thing we want to review is how ionic compounds react. If you have two ionic compounds that are in aqueous solution and you react them or mix them, they follow what's called a double replacement format type reaction. This is also called a double displacement or metathesis reaction. And essentially, you have your two ionic compounds where you have your cation and anions. And if you mix them, essentially what happens is our anions switch places. So instead of AB plus CD, you form AD plus CB. So back to our example here, if we reacted a sodium chloride with silver nitrate, we would end up essentially switching our anions, and we would get sodium nitrate, aqueous, and silver chloride. Now in this reaction, the sodium nitrate would be aqueous, and the silver chloride is the compound that may or may not precipitate out. You may want to review your general solubility rules in your textbook, and those generally tell us that things that contain ionic compounds that contain sodium, potassium, ammonium, nitrate, these types of compounds are generally soluble. However, something like a chloride that is paired up with silver, that is likely to be insoluble. So review your solubility guides a little bit from your textbook. If you find a compound that does not appear on the solubility guide, it's likely to be insoluble if the concentration of ions is high enough. So to discuss this or illustrate how to predict a precipitate, let's take a look at this problem. It says, will a precipitate form if we react or mix 0.15 liters of 0.1 molar lead nitrate, lead 2 nitrate, and 0.1 liters of 0.2 molar sodium chloride? If we mix those, will we get a precipitate? So there's a few steps that I like to follow to solve this type of problem. The first thing is let's write a chemical equation so we can see what products are going to likely form. So our two reactants, the question tells us, are lead 2 nitrate and sodium chloride. Both of these are aqueous. If we follow our double replacement type format, we should pair up the lead and the chloride and the sodium nitrate. We want to balance our equation just for completeness, and then we want to predict our solubilities. Sodium nitrate, that's going to be very, very soluble. However, lead 2 chloride is likely to form a precipitate. So this is the compound that we want to analyze to determine if this compound, the lead 2 chloride, will precipitate. And the question we really want to ask here as we move on is when we mix these two solutions, we're going to form lead and chloride ions. Is the concentration of lead 2 and chloride ions, is that going to be high enough to form a saturated solution where we get a precipitate? Or is it not to that critical point, so it will remain soluble? That's the question we want to analyze. So let's move on to our second step. Let's write a dissociation equation for the compound that may precipitate, and that would be our lead 2 chloride. So from here on out, this is the only compound that we're going to be concerned with. So if we write a dissociation equation, our lead 2 chloride would dissociate into lead ions and chloride ions, or vice versa, the lead 2 and the chloride ions would react to form the lead 2 chloride. That's probably the question we're asking here. Step 3, determine the concentrations of the lead and the chloride ion after our two solutions are mixed. Remember, if the concentration of lead and chloride ions in our solution, when we mix these two guys, if the concentration of lead 2 and chloride ions is very high, past our critical point, we'll get a saturated solution, we'll get a precipitate. If the concentration of lead and chloride is not high enough, and we'll discuss what that point is, if it's not high enough, then we will not get a precipitate. So let's determine our concentration of lead and chloride ions. Okay. So first, let's determine the moles of our cation, in this case lead. Okay. So how I did it, I took the volume of lead nitrate, because that's going to be my source of lead, and I multiplied it times the molarity, so my liters cancel. I end up with moles of lead nitrate. For every 1 mole of lead nitrate, it contains 1 mole of lead ions. So once I mix the solutions, I should have 0.015 moles of lead in solution. Next, let's determine the moles of the anion, or the chloride ion. Let's do the same thing. We take the volume of the sodium chloride. The sodium chloride solution is going to be our source of chloride ions. We multiply it times the molarity of sodium chloride. My liters cancel. For every 1 mole of sodium chloride, it contains 1 mole of chloride ions. And so our math tells us that we should have 0.020 moles of chloride in our solution. Now we're asked to determine the concentration. So concentration, of course, is moles divided by liters of solution. That would give us molarity. So let's divide the moles of cation, our lead cation, and chloride ions, which we just calculated, by the total volume. Remember, the total volume, we mixed 2 solutions. So we had 0.15 liters of lead nitrate. We mixed that with 0.1 liters of sodium chloride. So our total volume, after we mix them, is 0.250 liters. So we want to divide the moles of lead and moles of chloride by the total volume. Here's the lead divided by our 0.250 liters, and that gives us our concentration or molarity of lead ions. Same thing with chloride. Remember, we just calculated the moles of chloride divided by the total volume, and that gives us the molarity of chloride ions. Okay? So be sure you're writing these numbers down as we go, because we'll use them again later. So let's continue on with our problem. We know the concentration of lead and chloride ions in our new solution, our mixture. So determine if the ion concentration is high enough to result in a precipitation. How would we do that? Well, we need to write a QC expression. Remember, QC expression is essentially just an equilibrium expression, except our concentrations that we plug into our QC expression are not necessarily equilibrium concentrations. So QC, calculating QC, allows us to determine if the reaction, which is not at equilibrium, will proceed to the left or to the right. And one other thing, because we're dealing with precipitations, instead of calling it QC, it's often called IP. It's the same thing, but IP stands for ion product. So we want to write a QC or an IP expression, which would look just like an equilibrium expression or a KSP expression. So our IP is equal to the concentration of lead 2, times the concentration of chloride squared. We square it because we have a 2 here. So our fifth step, once we have our IP expression, we now want to plug in the concentrations of our ions. Remember, we just calculated our lead concentration and our chloride ion concentration, and we want to plug those in, and we want to solve for IP. Again, this is very similar to calculating QC. What did we do with QC? Remember, we compared it to KC, and that allowed us to determine which way the reaction would proceed. That's essentially what we're doing here. So if we solve for IP, we get an IP value of 3.8 times 10 to the minus 4. So our last step is we need to compare our IP to the KSP for lead chloride to determine the direction that the dissociation reaction will proceed. Will the reaction proceed to the left, or excuse me, to the right or to the left? Which way will it proceed? Well, we compare these two, and KSP, I got that from a table from my textbook. If you ever need a KSP value when you're working problems, again, please refer to the appendix in your textbook, which has KSP values for most ionic compounds. So when we compare these, what are we looking for? Well, we want to see if our IP is greater than KSP, then our concentration of ions is greater than the equilibrium concentration, and precipitation will occur. So if our ion concentration is greater than KSP, we have more than a saturated solution, we will get precipitation. If the two are equal, then a saturated solution exists and the solution is already at or exactly at equilibrium. And if if our ion product is less than KSP, then the concentration of ions is not high enough to result in precipitation. And precipitation, therefore, will not occur. So we saw that our IP value was greater than KSP, which means the concentration of lead and chloride is greater than the equilibrium concentration. So we will get a precipitation of lead chloride when we react our lead nitrate and our sodium chloride. So let's look at another problem. Remember, if you need a KSP value, you can refer to the appendix in your textbook or the internet. So read this problem, pause the video, follow the steps we just went over, and see if you can determine whether a precipitate will form. Pause the video and give it a try. Okay, so the first thing we need to do is what products are going to form here. So let's write our chemical equation and determine which of our products is likely to precipitate. We're reacting potassium sulfate with silver nitrate. So we're going to get silver sulfate and potassium nitrate. So here I have the balanced chemical equation. Potassium and nitrate salts are very soluble, but silver sulfate is possibly going to be the precipitate that will form. We have to analyze our concentrations of ions first, though. So next, let's write a dissociation equation for the silver sulfate. Remember, we're only concerned with the silver sulfate from here on out. So our silver sulfate is going to dissociate, or if it, or vice versa, the silver and the sulfate will react to form silver sulfate here. And since silver has a +1 charge, we're going to have 2 silvers for every 1 sulfate. So next, let's determine the concentration of our silver cations. We take the volume of silver nitrate that was given in our problem, multiply it times the molarity. Our liters cancel, we get moles of silver nitrate. For every 1 mole of silver nitrate, we should get 1 mole of silver. So we have our moles of 0.026 moles of silver. Next, let's figure out how many moles of the sulfate anion we have in our solution. The potassium sulfate, that's the source of our sulfate ions. So we take the volume that was given, multiply it times the molarity of potassium sulfate given. Our liters cancel, we get moles of potassium sulfate. 1 mole of potassium sulfate produces 1 mole of sulfate. So we should have 0.0052 moles of sulfate produced. Now remember, we want a molarity, not moles, molarity, so concentration. So we need to divide the moles of each by the total volume. We take the 2 volumes of our 2 solutions and add them together, and we get 0.825 liters total volume. So let's divide the moles of silver that we just solved for by the total volume to get the molarity of silver and the molarity of sulfate in our new mixture or our new solution. So once we have our 2 molarities, let's write an IP expression for the dissociation of silver sulfate. Our IP is going to equal to the concentration of silver squared, don't forget that, times the concentration of sulfate. Okay. Substitute in your concentrations that we just calculated for silver and for sulfate. Don't forget to square it. Solve for IP. We get 6.5 times 10 to the minus 6. Again, IPs and KSPs, they don't have any units. So sixth, let's compare IP to our KSP. Remember, we got the KSP from our table in our textbook or from the internet. And we can see here that our IP value is less than our KSP. So our concentrations, essentially our ion concentrations of silver and sulfate, have not reached saturation level. They're below our KSP value. So that tells us that IP, since ISP is less than KSP, we have an unsaturated solution. Precipitation will not occur. So here we will not get any silver sulfate precipitating out of solution. So essentially no silver sulfate forms. So be sure you're familiar with these steps, understand why we do each step, and be sure you can solve problems similar to this. So practice some more of these from your text.